Swayam Prabha. Digital India. Educated India.
So, in the last lecture I have discussed that how we can determine the water table position for sandy soil and for the clayey soil. Now, today I will first discuss about the how we can determine the water table position for clayey soil by using one example problem. So, this is the expression by which we can determine the water table position of clayey soil by using piezo cone. So, now one example problem I want to show that suppose we have a ground this is the ground surface and this is the borehole. Now, at t equal to 0, this is the initial water table position. Okay, at t equal to 0, and that distance from the top say 7 meter. Okay. So, that distance of initial water table position within the borehole is at t equal to 0 is 7 meter from the ground surface, and then at with time the distance of the water table from the ground surface is measured and the rise of the water table within the borehole is measured. So, this is say at t 1 equal to 24 hours, this is the position. So, this is a t with some time t 2 is say 48 hours, and then this is the time t 3 for 72 hours and so on. And then this distance is say with some distance is del h 1 which is say 0.9 meter and del h 2 is another distance. Okay, so, now we will get h 0 which is from base to that water table position. Suppose this is the water table position. So, this is h 0. So, this is the h 0 which is water table position from the initial water position at the borehole. So, h 0 expression we know that del h 1 square divided by del h 1 minus del h 2. So, we can put some value, say this is del h 2 is 0.7 meter. So, we can put that 0.9 square divided by 0.9 minus 0.7 say. So, this will be roughly 4 meter. So, this we can, so now we know that this is the 7 meter. So, this is roughly 4 meter. So, this distance will be roughly 3 meter. So, this way we can determine the position of the water table from the ground surface. Okay, so, now for cross check that, so we can calculate again the H2, which is del H2 square divided by del H1 minus del H2. So, that will be del H2 square is 0.7 square minus 0.9 minus 0.7, which is also 2.45 meter. Similarly, del H3 also del H3 square divided by del H2 minus del H3. So, this way then we will get another value. So, this value also del H2 is from here to the water table position, and del H3 is from here. So, when you calculate the del H2, then del H3 also, all the position should be at this line. Okay. So, that means this way we can determine the position of the water table from the ground surface also. So, this way we can determine the position of the water table from the ground surface. Now, in the next part that I will start about the geophysical exploration. So, first I will discuss about the seismic reflection survey, then seismic refraction survey, then seismic cross-hole survey, and then resistivity survey. So, now what is seismic reflection survey? So, in the seismic reflection survey we have one source on the ground surface. Suppose this is the source on the ground surface, and these are the geophones, or these are called receivers. So, this is the source, these are the receivers, and then we generate one source. So, that source will create a wave, and this wave will reflect from the interface between two layers or the hard strata, and then it will go back to the receiver. So, that means from here source, this is the source, it is coming in this direction, then it is moving back. Okay. Then also it is coming from this direction, then it is going back. So, now from the source there will be n number of waves will generate, but depending upon where you are placing the geophone, that rays are drawn. So, there will be, if I put n number of geophones, then these waves will be received by the geophones from the source. Now, there is the two way these waves can travel from the source to receiver. One is the direct wave, which will travel from the source to the receiver. This red one is the direct wave. So, it will travel from source to the receiver, and then another will reflect from the layer interface, then it will go back to the receiver. So, this is the direct wave, red one, and this black one is the reflected wave. And then based on that we can determine what would be the thickness and properties of this soil layer. Now, so now there are the two waves, as I discussed, that there will be two waves will be generated. One is the direct wave, another is the reflected wave. So, the expression of the direct wave, so suppose this is the direct wave, or we can say this is my source and this is the receiver. So, the direct wave, this is the T d, and this is the distance x. So, if the velocity of the first layer is V p, velocity of the wave, then the T d will be x divided by V p 1. Okay. So, this is the expression of the T d, and the T r, which is the reflected wave. So, that T r expression also you can get by this expression. This is 2 root over a square plus x by 2 square B p 1. So, where h is the thickness of the layer. So, this is one particular case. Now, if I put n number of geophones, say suppose this is the position of the first geophone, which is x1, this is the position of the second geophone, this is the position of the third geophone, and so on. There will be, this is the position of the nth geophone. So, all the geophones, there will be one direct ray, one reflected rays. So, now if I put the data of the all geophone in a graphical form, that means this x axis, this is the x distance, and y axis is the time. Okay. So, now the two waves will be reached from in each geophone. So, this is the, for every geophone the direct ray equation is x divided by Vp1, and Vp1 will not change because it is the same soil layer, only the distance will change, and this is the a straight line equation is the equation 1, which is a straight line and it is passing through the origin. So, this is the equation 1, which is the direct wave, which is the straight line passing through the origin. Okay. And equation 2 will give us equation a line which is not the straight one. Okay. So, it is the nonlinear type of equation. So, we will get one graph. So, that is the reflected wave graph. So, that means what we will do? We will plot the travel time for direct ray and distance, travel time for the direct ray for different geophone and the corresponding distance, that we will do draw. So, this will give us the equation number 1 and this will give us the equation number 2. So, again we will draw the travel time of the reflected waves and then the distance, corresponding distance. So, this way we will get these two curves. Now, that means in this survey we have to measure the travel time of two waves, one is the direct wave, another is the reflected waves. Now, from here this equation 2, if I put x equal to 0, if I put x equal to 0, then my TR will be equal to 2h by Vp1. So, this is the value 2h by Vp1 at x equal to 0. So, this is the value x equal to 0, TR is equal to 2h by Vp1. Now, from this equation number 1, the slope will give us 1 by Vp1, because this is the slope 1 by Vp1. So, from equation number 1 I will get the velocity of the layer, and from equation number 2 put x equal to 0 I will get the TR. So, that TR or TR 0 you can see. So, this TR 0 I will measure from here. So, I will extend this line, and because it may not start from x equal to 0, it may start with some value of x, but you have to extend that line and make it 0. So, once I get the make it 0, this is maybe the intersection point of the curve to the t axis, and that time is corresponding time is TR 0. Okay. So, that TR 0 is equal to 2h Vp 1. So, now from here I can get h equal to TR 0 Vp 1 divided by 2. So, from this equation I know Vp1 that I will get from the equation number 1 or the straight line curve, and then I will get TR 0 from this curve intersection point, and then I will get the thickness. So, I will get the thickness of the layer and I will get the velocity of the wave also. So, now why I am taking number of points? Because if I take one particular data, then there is a possibility of error. So, to reduce that error or to minimize that error, we can take n number of geophone, and then that data we can plot in a graphical form, and then from that plot I can get the required properties, that is the velocity of the wave and thickness of the layer. So, this is the h that I will get. So, now I am putting h equal to x equal to 0. So, that will give us this x equal to 0, this will give TR 0. So, which is nothing but half into TR0 VP1, which is the same expression that I have given. So, now one problem is that in this seismic reflection survey, we have to measure two waves. That means, we have to measure the direct waves travel time, and then we have to measure the reflected wave travel times. So, that means it is difficult to identify which one is the reflected wave, which one is the direct wave, because it is difficult to measure these two waves. So, to remove that limitation, the seismic refraction survey can be conducted, where we have to measure only the first arrival time of the wave. That means, we will to measure the travel time where the wave is received by the geophone first time. So, that means, we will measure the only one wave that will receive by the geophone first. Okay. So, that is the advantage of this survey, seismic refraction survey over the reflection survey. And another issue is in the reflection survey, we are measuring the thickness of the top layer. Okay. But in the seismic refraction survey, we can measure the thickness of n number of layers also. Okay. So, here your methodology is the same, because here this is the source and these are the position of the geophones. So, again from the source there will be direct rays, there will be refracted rays also. If there is a n number of layers, then there will be n number of refracted rays. Okay, because these refracted rays, this is the interface from the top first layer and the second layer. These refracted rays, this is the interface between the second layer and the third layer. So, that means, if there is a two layer system, then we will get one refracted rays and then one direct rays. So, but we will note down, or we require to measure the only first arrival time of the wave. So, that means, and if there is a more than two number of layers, then there will be more than one number of refracted rays. So, now, this is one particular case that I was discussing. So, this is the this is the source, A is the source, when direct ray will go to C and D, because C and D is the position of the receiver. Then one refracted ray will go to the C point, another refracted rays will go to the D point, and this is the case for three layer system. That means, this is the layer 1, this is layer 2 and this is layer 3. And one thing is that now if I have one layer, this is the two layer. Now, this is the ray that is coming in the interface of the first layer and the second layer. Now, suppose you have a velocity of Vp1 for the first layer and Vp2 for the second layer. Now, if your Vp2 is greater than Vp1, then what will happen? These refracted rays will go away to the normal. But if Vp2 is less than Vp1, then refracted ray will travel towards the normal. So, now under the second condition, if refracted ray travels towards the normal, then there is no possibility that this ray will reach to the ground surface again and it will be measured by the geophone. Because what I am saying, that if this is the ray, so if this ray is, because this is the, now if this ray moves in this direction, then it will never reach to the ground surface. So, that means, to reach to the ground surface, these rays has to move away from the normal. Okay. So, and that is only possible if this first condition is satisfied. That means, Vp2 is greater than Vp1. So, this is one of the limitations of this test, is that this test will give us the proper result if the velocity of the second wave is greater than the velocity of the third wave or first layer wave. Or if there is 3 layer system, then the Vp3 should be greater than Vp2 should be greater than Vp1. So, that means, and when this velocity of the rays is function of the density, that means is density increases, then velocity of the wave will also increase. Okay? So, that means the velocity of the wave is more for denser soil compared to the loose soil. So, that means, which indicates that this survey will give us the proper result if the density of the soil layer increases as depth increases. That means the density of the third layer should be more than the density of the second layer, and the density of the second layer should be more than the density of the first layer. So, then only I will get the good result. So, and in other way, the velocity of the third layer should be greater than the velocity of the second layer, and velocity of the second layer should be greater than the velocity of the first layer. Then only I will get the good result. So, that means, as I am saying that now there is a possibility that this ray will travel in this way, and this is only possible if this angle is the critical angle. So, that means, if the angle at which these V1 rays is intersecting the first layer and the second layer interface with an angle critical angle, then only it will travel with parallel to the ground surface, and then it will go to the second geophone. So, that means, this angle is critical angle. So, this way here I will travel, this geophone will measure the first arrival time of the wave, and now if I put again, if I take n number of geophone data and if I draw them, in x axis is the distance and y axis is the time, then I will get this type of plot. So, every change in slope indicates the change in soil layer. So, here in the given plot there is a 3 slopes. So, that means, which indicates that there are 3 layers. So, this is the layer 1 velocity, this is the layer 2 velocity, and this is the layer 3 velocity. Okay. So, slope of this curve will give us the velocity of 1/y velocity of the each layer. This is the slope is 1 by Vp2, this is 1 by Vp3. So, this is the slope. Okay. So, this way I will get the velocity of this each layer. So, that means, if there is a change in slope, that means the change in layers, and you have to calculate the velocity of the each layer. So, this way this slope will give us the 1 by velocity of that layer. So, this way I will get the velocity of the each layer. Now, as I mentioned here, the first arrival time we have to measure. So, now if you look at this figure from A to C, so there is a possibility, as I mentioned, there will be direct rays and there will be a refracted rays, and if there is a number of layers, then there will be number of refracted rays. Now, which ray will reach first? Now, so initially if you see that initially definitely that from A to C, if the distance between A to C is very small, then definitely direct ray will reach first, because the travel distance is very small. But as the distance between A to C increases, then the refracted rays will reach first. Why? Because the travel distance will again increase, whether the your distance is small or large. But as the distance increases between A and C, then this portion will also increase. That means, the portion at which the wave will travel with a velocity of Vp2. So, that means, here from A to say E, the wave will travel with a velocity of Vp1. From E to F, it will travel with a velocity of Vp2.
again from F to C it will travel with a velocity of Vp1, because this is the interface between second layer and the first layer. So, it will travel with a velocity of Vp2, and the Vp2 is greater than the Vp1. So, the travel time will decrease as the distance between A to C will decrease, because as the distance between A to C will decrease, then the wave, the distance the wave will travel with a velocity of Vp2, that will also decrease. So, that means the travel time will decrease. So, there will be a point at which initially if we keep on increasing the distance between A to C, that means the source and the geophone, initially the direct ray will reach first, okay. But after a certain time or certain distance, your refracted ray will reach first compared to the direct ray, because direct ray will always travel with a velocity of Vp1, but refracted ray will travel with a velocity of some portion is Vp1, some portion is Vp2 and some portion is again Vp1. Now, if the portion the wave is traveling with a velocity of Vp2 increases, then the travel time will decrease. So, ultimately there will be a point at which the direct ray and the refracted ray will reach at the same time. So, that distance from the source is called the critical distance. So, from the graph you will find the point where there will be a change in slope. So, corresponding that distance will give us the critical distance. So, this distance is called the critical distance. So, similarly there will be another critical distance. So, this I can say xc1, this is xc2. Now, what is the difference between xc1 and xc2? So, now if you put any geophone within the distance of xc1, then your direct ray will reach first. If you put a geophone within the distance xc1 and xc2, then the refracted rays passing through the interface of first and second layer will reach first. Now, if I put any geophone beyond the distance xc2, then the refracted rays travel to the interface between second and third layer will reach first, because again the third layer wave velocity is greater than the second layer. So, that means every point this change of slope will give me a critical distance. So, that which indicates that which refracted rays will reach first. Okay. So, now the equation that I am giving for two layer case. Two layer case, your TD expression is x by Vp1, x is the distance from the source to the geophone, then Tr refracted rays, that is x Vp2 plus 2h1 root over 1 by Vp1 square 1 by Vp2 square. So, this is the second case. So, now you can see that this is the equation of direct rays and the refracted rays. So, from this equation you can see the slope of this, because the if you put the geophone within the xc1 distance. So, definitely within that zone the equation 1 will be applied, and between xc1 and xc2 equation 2 will be applied. So, that means you can see the slope will give 1 by Vp1 and this slope will give 1 by Vp2. Okay. So, now how we can determine the distance x1? So, again if I extend this line, so this will give us Tr01. Okay. So, now Tr01 is the time at x equal to 0. Now, if I put x equal to 0, so Tr01 will be 2h1 root over 1 by Vp1 square by 1 by Vp2 square. or the H1 I can calculate is equal to T0 or TR01 divided by 2 Vp1 Vp2 root over Vp2 square minus Vp1 square. Okay. So, this equation we can use and we can get the expression of H1. So, this way we can get the thickness of the first layer. So, that means that this slope will give us the velocity of the corresponding layers, and if I put the velocity and if I know the this T01 from the graph, then I will get the H1 thickness. This is one way. In the another way also I can get the thickness H1, that is that we know, as I mentioned, that at the critical distance the direct rays and the refracted rays will reach at the same time. So, this is the critical distance XC1. So, at this critical distance my TD is equal to TR at x equal to XC1. Okay. So, now if I put that one, I can write that XC divided by Vp1, that will be equal to XC1 divided by Vp2 plus 2H1 then root over 1 by Vp1 square root over 1 by Vp2 square. Okay. So, now here also that Vp2 Vp1 is known, Xc1 I will get from this plot, then only unknown is H1. So, again here H1 expression will give us that Xc1 by 2 root over Vp2 minus Vp1 divided by Vp2 plus Vp1. So, this is the whole root. So, either you can use these expression in terms of TR01 or you can use Xc1. So, both way you can determine the thickness of the first layer. So, this is H1 is the thickness of the first layer, you can say Z1 or H1, here also Z1 or Z2 or H2. So, next class I will discuss about the 3 layer case, because this is the 2 layer case I have discussed. In the next class I will discuss about the 3 layer case. Thank you.